Hello, and welcome to my presentation on Xray Computer Tomography for material parameterization. My name is Aaron, and I'm a PhD student based at UCL within the Electrochemical Innovation Lab. And in this video, I will discuss some of the uses of tomography and how it can relate to electrochemical modeling. In this video, I will go over what X-ray tomography is, how it works, and why it is useful. We will then look into some of the parameters that can be gained from it. Finally, I will discuss its application on a range of commercial electrodes, all with different mass loadings, before looking at some future in-situ work. X-ray computer tomography. It is a non-destructive method of imaging, utilizing high-energy photons that can pass through materials that visible light cannot. Doing so enables the generation of 3D images from a range of samples. Within the Electrochemical Innovation Lab, we have three different X-ray machines, the Nikon, Versa, and the Ultra. This enables us to image samples ranging in size from 1 meter all the way down to 64 microns. As the sample size decreases, we can achieve superior resolution, down to 64 nanometers for the ultra-large field of view. This presentation will focus on the circled region, with sample sizes ranging from 200 microns down to 64 microns. X-ray tomography works by taking hundreds of images of our sample as it rotates through 360 degrees. Since every element attenuates X-rays differently, the number of X-ray photons that pass through the sample will vary with each projection. Once all the images are taken, we can filter and then back project the results to form a 3D render of our sample. Superior image resolution can be achieved by combining geometric magnification with optical magnification, as can be seen on the screen now. This is done through the use of lenses, which is what our Versa, which is our micro-CT scanner, does. The image on the left of the screen is a 1D slice through a 3D volume from a 200 micron diameter disc. Due to the large sample size, a large number of particles and a large electrode volume can be characterized. This gives better statistics and enables a more accurate representation of the material as a whole. By imaging in the Ultra, a much smaller volume is studied in greater detail. As you can see here, finer details within the particle can be seen, such as internal voids and particle cracking. Furthermore, imaging with this higher resolution enables three-phase segmentation, with the binder phase also being visible. Once our scans are complete, we can segment each phase as shown in this image. Here, a grayscale volume has been segmented into particles, and then each particle has been separated into a unique label field. This enables each individual particle to be characterized and can give an indication of the morphology of the electrode. Image segmentation and separation is not always perfect, and as such, machine learning is being utilized to improve the quality of these operations and enable more accurate results to be generated. Model parameterization. The segmented data can be quantified for P2D style models. These models are relatively simple and fast to run. However, they require specific parameters from the electrode to operate. Post-segmentation, some of these parameters can be calculated, as shown below, giving an average value for the electrode, which can then be fed into the model. More complex 3D models enable the modeling of the real-world microstructure. This is done by creating a mesh of the X-ray scan, usually done in simpleware. This enables the model to be more accurate, as average values are not required. However, these models are much more computationally expensive and often are only run on small volumes. Moving on to the commercial cathodes, we have a range of mass loadings from 1 to 4 mAh per centimeter squared, which have all been imaged at 2-length scales with the aim of characterizing their morphology and aiding in the full parameterization of the cathodes. Furthermore, as mass loading increases, the rate capability of an electrode decreases, and with the use of CT, it can be investigated as to whether this decrease is due to changes in the electrode structure or due to the increased diffusion distances. In this slide, we can see all of the CT scans that have been completed for all of the mass loadings. The top row is our micro-CT scans, and the bottom row is the nano-CT scans. The thickness difference is clear to see across all of our samples, and through segmentation and analysis of each of these scans, we can look for any differences across the samples. Initially, we can find the volume fraction of the particles from each electrode, with all samples giving a value of around 60%. there is a slight decrease in volume fractions as the electrodes get thicker. Next, we can look at the particle sizes with an expected value of 6 microns. The Versa results are slightly larger than this, potentially due to the inclusion of binder within the segmentation stage. The Nano CT results give a lower than expected value, likely due to large particles being split into several smaller ones at this length scale. Overall, the diameter, as with the volume fraction, is relatively constant across the different mass loadings. Finally, the tortuosity can be calculated using the MATLAB plugin tau factor. Doing so gives an indication of the transport properties of each electrode, with the micro CT data showing very similar results across each sample. The nano CT data shows significantly more variation, potentially due to the choice of volume chosen, and the inclusion of micropores within the particle increasing. However, although small variations are present, on the whole, each electrode has a similar tortuosity, and therefore it would be expected that any mass transport limitations are due to the increased thickness as opposed to a change in the microstructure. To summarize, X-ray tomography is a non-destructive imaging tool that can be used to parameterize P2D style models as well as provide 3D meshes for image-based modeling. Mass loading appears to have very little impact on the microstructural properties of the electrode, indicating that differences in rate capability are due to increased distance of diffusion as opposed to changes in the microstructure. Finally, looking forward, the inclusion of in-situ imaging will enable the changes of microstructure and particle health to be assessed as a cell cycles, enabling models to better predict how and when a cell might fail. Thank you for watching, and if you have any specific parameters that you require for your models, please do send us an email.